Hi, I'm Alex. What if scattered across the cosmos, there are things that openly break the rules of stars, planets, gravity, and time, not as rare mistakes, but as exceptions the universe quietly permits? Tonight, we confront 42 cosmic anomalies, objects that should not exist, should not survive, yet undeniably do. If this kind of exploration draws you in a soft like or subscribe, helps keep these journeys alive. Now let's begin. Somewhere out there, floating in the cold, black nothing of space, there's something impossible. It's the size of a planet. It weighs more than our sun, and it's made of pure diamond, not a metaphor, not science fiction, an actual literal diamond. Astronomers have found it. They've measured it, and it's real. Its name is BPM 37093, but scientists nicknamed it something way more appropriate, Lucy, after the Beatles' song Lucy in the Sky with Diamonds, because that's exactly what it is, a diamond in the sky. Here's how this cosmic gemstone exists. When a star like our sun runs out of hydrogen fuel, it expands into a red giant, sheds its outer layers, and what's left behind is the core, a white dwarf, super dense, super hot. Over billions of years, these white dwarfs cool down, and the carbon inside them begins to crystallize, just like diamonds form under pressure on Earth. Only this isn't a tiny rock on a ring. This is a crystallized sphere, roughly the size of Earth, weighing more than the entire sun, made of solid carbon crystal. That's Lucy. And get this, its diamond core is estimated to be 10 billion trillion carats. That's a 1 followed by 34 zeros. If you could somehow mine it, spoiler, you can't, you'd be the richest person in the universe. Except you wouldn't. Because if you actually brought that much diamond to Earth, the global economy would collapse instantly. The value would drop to zero. Think about it. All the diamonds on Earth combined, they're a single grain of sand on Lucy's beach. One grain. That's how big this thing is. And here's the wildest part. We know it's diamond because of asteroseismology. Scientists measure how the star vibrates as it cools, kind of like starquakes. These vibrations reveal the internal structure, like how seismologists study earthquakes to learn about Earth's interior. In Lucy's case, the data lined up perfectly. The star had crystallized, and when you listen to those vibrations converted to audio, you're hearing the ringing of a planet-sized bell, a diamond bell, floating in space. But Lucy isn't alone. In 2011, astronomers found a planet-sized diamond orbiting a pulsar, a dead neutron star. This diamond planet, about 5 times the size of Earth, whips around its pulsar once every 2 hours. That's right, a diamond planet doing laps around a corpse sun at breakneck speed. And our own sun, in about 5 to 7 billion years, it'll become a white dwarf too. Then after another few billion years, it will cool and crystallize. In other words, the future corpse of our sun will be a diamond. Think about that. Everything we know, Earth, the moon, all of it, once orbited a yellow star. And someday, it'll orbit a crystallized jewel in space. These stars shouldn't exist, at least not in the way we think about stars. We imagine them as burning gas balls, not silent frozen gemstones glowing with ancient heat. But they're out there, and there could be billions of them in our galaxy alone. Lucy isn't rare. She's just the beginning. Now let's flip the script completely. Because while Lucy is a frozen diamond, there's a planet out there that's hotter than the very star it orbits. Let that sink in. A planet hotter than a star. It sounds backwards, like finding ice cubes that melt fire, but it's real. It's called Kelt 9b, and it breaks every rule. Kelt 9b is a gas giant like Jupiter, but that's where the similarities end. This thing orbits so close to its star that it completes a full lap every 1.5 Earth days. It's practically skimming the surface, and the star Kelt 9 is already no slouch. It's a blue, A-type star, hotter and more massive than our Sun. But the planet is so close that it gets blasted with over 4,000 times the radiation Earth receives. The result, the planet's dayside temperature hits 4,300 degrees Celsius. That's hotter than 70% of all stars in the Milky Way. It's hotter than red dwarfs, hotter than the surface of some suns. And it's not even made of fire or fusion. It's just a planet being scorched by proximity. The heat is so extreme that molecules can't exist on the dayside. Not water, not clouds, not even hydrogen molecules. The atoms themselves get ripped apart. The atmosphere becomes a churning soup of individual atoms: iron, titanium, hydrogen, all boiling in the heat like a cosmic cauldron. And Kelt 9b is evaporating. Its atmosphere is literally being blasted off into space by ultraviolet radiation. Scientists estimate it's losing millions of tons of material every second. Over time, it might vanish completely, boiled down to nothing. Think about the next time you complain when the temperature hits 95 degrees Fahrenheit in summer. Kelt 9b is dealing with temperatures over 700 degrees Fahrenheit. And it's not just surviving, it's holding itself together. Barely. But if you think Kelt 9b is insane, just wait. Because there's a planet out there where it rains glass. Sideways. At supersonic speeds. HD 189733b looks beautiful from a distance. Deep blue. Serene. Almost like Earth, floating in space. It's one of the most stunning exoplanets ever photographed. But that beauty is a complete lie, because HD 189733b is hell. This planet orbits its star once every 2.2 Earth days. It's so close that its atmosphere is superheated to over 1,200 degrees Celsius. And the winds. The winds scream across the planet at more than 8,700 kilometers per hour. That's Mach 7, 7 times the speed of sound. These aren't breezes. These are supersonic hurricanes that never ever stop. But here's where it gets truly alien. The planet's atmosphere contains silicate particles, tiny glass-like grains suspended in the high-altitude clouds. At such high temperatures, these silicates condense into droplets of molten glass. Then gravity pulls them down, except they don't fall straight. Because the winds are so fast, the droplets travel sideways, slashing across the atmosphere, like microscopic razor blades at hypersonic speeds. Imagine standing in a hurricane, where instead of water, the wind throws molten glass at your face, sideways, at speeds that would shred a fighter jet. That's HD 189733b. There is no weather warning system for that. There is no shelter. There is only instant annihilation. Simulations show that if a human somehow stood on the surface, they'd be torn apart in less than 0.1 seconds. Not by the heat alone, not by the pressure, but by millions of glass shards moving faster than bullets, shredding every molecule of your body before you could even process what was happening. And here's another weird detail. The hottest point on the planet isn't directly under the star where you'd expect it to be. It's shifted eastward by thousands of kilometers. This phenomenon, called hotspot shift, happens because those supersonic winds transport heat so efficiently that they push the thermal maximum away from the substellar point. The wind literally moves the heat before it can settle. Oh, and if you were somehow close enough, say 100,000 kilometers away, you might be able to smell it. The sulfur compounds in its atmosphere could theoretically reach your spacecraft. So, not only would you see a beautiful blue planet, you'd smell rotten eggs right before the glass storm killed you. But HD 189733b isn't the strangest planet when it comes to appearance, because there's another world out there that takes strangeness to a whole new level. A planet so dark, it makes coal look shiny. Meet Taura-ES 2b, the darkest planet in the known universe. Most planets reflect at least some light. Earth reflects about 30% of incoming sunlight. Because of clouds, oceans, and land, even gas giants like Jupiter and Saturn reflect a decent amount due to their thick cloud layers. But TRES 2b, it absorbs over 99% of the visible light that hits it. Its reflectivity, or albedo, is less than 1%. That's darker than charcoal, darker than acrylic paint, darker than anything you've ever seen. TAR-ES 2b is a hot Jupiter orbiting extremely close to its star, about 750 light-years away in the constellation Draco. It completes a full orbit in just 2.47 days. The proximity heats the planet to over 1,800 degrees Celsius. At these temperatures, most molecules break apart. Cloud formation becomes nearly impossible, and the atmospheric chemistry changes in bizarre ways. Scientists believe the darkness comes from light-absorbing molecules in its atmosphere. Gaseous, sodium, potassium, and titanium oxide. These substances absorb visible light incredibly efficiently, especially in the red and yellow parts of the spectrum. And because there are no reflective clouds, no ammonia hazes, no water vapor, nothing bounces light back. The planet just swallows it whole. And get this, TAR-ES 2b doesn't have a normal atmosphere. It has what's called a thermally inverted atmosphere. In most planets, temperature decreases as you go higher, just like on Earth. But on TAR-ES 2b, it's backwards. The higher you go, the hotter it gets. High-altitude compounds absorb starlight before it reaches the lower atmosphere, trapping heat at the top and creating this inverted temperature profile. So here's what you'd see if you looked at TRES 2b directly: a faint, ghostly red glow. Not from reflected light, but from thermal emission. The planet is so hot, it glows like a piece of metal in a forge. But in visible light, it's almost invisible. A shadow, a silhouette against the blackness of space. If you replaced Jupiter in our solar system with TAR-ES 2b, it would be nearly invisible to the naked eye. You might catch a faint red shimmer if you knew exactly where to look, but otherwise nothing. Just empty space where a planet should be. Imagine painting your house with the darkest black paint in the world. Vanta black, maybe. You'd think that's as dark as it gets. Then you see TAR-ES 2b and realize your paint looks like light gray in comparison. That's how dark this thing is. The next time you complain about bad weather, remember this. At least it's not raining molten glass sideways at Mach 7. At least the sky isn't swallowing 99% of all light like a cosmic black hole. At least you're not being shredded by supersonic wind-borne razor blades while suffocating in 1,800-degree heat. These planets break every rule we thought we understood. They shouldn't exist. Not like this. Not with weather that defies physics textbooks and atmospheres that laugh at our models. But they do exist, and they're out there right now, doing impossible things in the endless dark. But if you think glass rain and shadow planets are crazy, just wait, because there's something even more insane. A star that survived a supernova exploding right next to it. Imagine standing next to a volcano, not just any volcano, an apocalyptic supervolcano containing the force of several octillion nuclear bombs. Now imagine it explodes right next to you, and somehow you survive. You're burned, scarred, blasted away at insane speeds, but you're alive. That's exactly what happened to LP-4365, a star that got hit by a supernova and lived to tell the tale. This stellar survivor is located about 2,000 light years from Earth. At first glance, it looks like a normal white dwarf, a small, dense stellar corpse glowing faintly with leftover heat. But when scientists looked closer, the weirdness piled up fast. First red flag. It's moving way too fast. This little white dwarf is blazing out of the galaxy at over 850 kilometers per second. That's nearly 2 million miles per hour. Fast enough to escape the Milky Way entirely. In cosmic terms, it's making a clean getaway. Second red flag. Its chemical composition is all wrong. Normal white dwarfs are made mostly of carbon and oxygen, but LP-4365, it's full of heavy metals, iron, nickel, manganese. These are elements that usually form in supernova explosions. It's chemically scorched, like it went through a nuclear furnace. So scientists pieced together the puzzle. This star was part of a binary system, two stars orbiting each other closely. One of them exploded in a Type Ia supernova, a catastrophic detonation that usually vaporizes everything nearby. But instead of being obliterated, LP-4365 was somehow flung away from the blast. Not just flung. It absorbed part of the explosion, got its outer layers burned off, changed its chemistry completely, and kept going. It's like standing next to Mount Vesuvius when it erupts, getting caught in the pyroclastic flow, and then just walking away, charred, traumatized, but alive. Here's what probably happened. In the binary system, both stars were white dwarfs, orbiting each other. One was more massive. As they spiraled together, the massive one reached critical mass and detonated. But the explosion was asymmetric, off-center. One side blew up. The other side, LP-4365, got hit by the shockwave-absorbed radioactive material, lost its outer layers, and ricocheted away at escape velocity, half destroyed, half ignited, fully ejected. And LP-4365 isn't alone. Astronomers have since found others like it. Stars with similar velocities, strange compositions and burn scars from ancient explosions. There may be a whole population of these supernova survivors scattered across the galaxy. Ghosts of past detonations shot from their systems at insane speeds, now wandering alone through the void. This star is headed out of the Milky Way entirely into intergalactic space. In a few 100 million years, it'll be beyond the reach of even our most powerful telescopes. Alone, exiled, drifting forever in silence. But if you think a star surviving a supernova is extreme, let me introduce you to something even more unhinged. A star that spins so fast, it's basically a cosmic buzzsaw. Meet PSR J1748 2446 AD, the fastest spinning object in the known universe. This neutron star rotates 716 times per second, not per minute, per second. That's 43,000 revolutions per minute. Faster than a dentist's drill, faster than any engine, faster than anything humanity has ever built. And it's doing this with the mass of the sun, packed into a sphere just 20 kilometers wide. Let that sink in. This object is so dense that a single teaspoon of its material would weigh about 1 billion tons. It's made almost entirely of neutrons, crushed so tightly that atoms can't exist in their normal form. Electrons and protons have fused together. What's left is pure nuclear matter, a solid ball of dead star spinning faster than anything else in the cosmos. And it's not just spinning for fun. Its surface is moving at 1/4 the speed of light. If it spun even one rotation per second faster, it would tear itself apart from centrifugal force. It's right on the edge of rotational breakup, the theoretical maximum speed a neutron star can spin without flying to pieces. And it's holding together, barely. So, how does something spin that fast? It starts with theft. These neutron stars, called millisecond pulsars, often orbit a companion star. Over millions of years, they pull gas off that companion, forming a swirling disk of material that rains onto the neutron star's surface. This process transfers angular momentum, accelerating the spin. The more matter it steals, the faster it spins, until it's whirling at speeds that almost break physics. If you could somehow listen to PSR J1748 or 24468 converted to audio, you'd hear 716 ticks every single second, a rhythmic pulse so fast it sounds like a continuous scream. You're hearing the heartbeat of a dead star, ticking faster than any drummer's hands could ever move. And here's the kicker. We use these things for navigation. Millisecond pulsars are so precise, so consistent, that some researchers are developing systems to use them as galactic GPS, a network of spinning corpse stars guiding spacecraft through deep space. By this point in the story, you might think I'm making this up. You might think this is science fiction, but this is real science. Measured, confirmed, published in peer-reviewed journals, and completely insane. The next time your car's tachometer hits 7,000 RPM and you think that's fast, remember there's something out there spinning 6 times faster, and it's the size of a city. But hold on, if stars can spin like maniacs and planets can self-immolate, what about galaxies? Turns out there's a galaxy out there with no dark matter, and that's supposed to be impossible. This galaxy is called NGC 1052 DF2, or just DF2 for short. From a distance it looks faint, wispy, unremarkable, but it's one of the strangest things we've ever found in the cosmos. It shouldn't exist, not by the rules we've been following for decades. DF2 is an ultra-diffuse galaxy located about 65 million light-years away. It's roughly the same size as the Milky Way in diameter, but it has 1/200th the number of stars. Imagine a ghost version of our galaxy. Same size, barely any substance. Like someone blew up a balloon and forgot to put anything inside. At first, scientists thought this was just another strange, faint galaxy, but then they studied its star clusters, tightly packed groups of stars that orbit around the galaxy. The key was measuring how fast those clusters were moving. If there was a lot of mass hidden in the galaxy like dark matter, then the clusters would be moving fast, pulled in tight by gravity. But they weren't. They were moving slowly, way too slowly for a galaxy of that size, unless it had almost no dark matter at all. In other words, the stars were held together only by the visible matter. No extra gravity, no dark matter halo, just plain old baryonic matter. What we can see. That was unprecedented. Every galaxy we've ever studied seems to have dark matter as a fundamental component. It's what keeps stars from flying off into deep space. Without it, galaxies simply shouldn't form, at least not like this. So DF2 immediately broke the rules. Naturally, there was skepticism. Maybe the measurements were off. Maybe the galaxy was closer than we thought, which would change the calculations. Maybe we were missing something. But then in 2019, scientists found another galaxy with the same properties, NGC 1052 DF4, a twin to DF2, just a little farther away. Same ghostly structure, same lack of dark matter. It wasn't a fluke. These galaxies truly seem to exist without dark matter, which is a huge problem, or maybe an opportunity, for astrophysics. Because up until this point, dark matter was non-negotiable. Every galaxy needed it. We couldn't detect it directly, but we saw its gravitational effects everywhere. Galaxies rotating faster than they should, light bending around invisible mass, clusters held together by unseen glue. So how does DF2 stay together? Here's the thing, it barely does. The stars in DF2 are spread out and dim. It's a translucent wisp of a galaxy, fragile, tenuous, almost falling apart. It's like someone accidentally assembled a galaxy and forgot to use glue, and yet it's been floating around in space for billions of years. One theory is that DF2 formed in a violent interaction. Maybe a larger galaxy stripped away its dark matter, leaving just the bare, luminous core behind, like peeling an orange and throwing away everything except the thin membrane. Another theory suggests it formed in an unusual environment where dark matter was never dense to begin with, like building a sand castle in the shallows instead of on the beach. And then there's the truly wild possibility. What if this is telling us dark matter isn't universal? That maybe not every galaxy needs it? That the rules aren't as fixed as we thought? It could even support alternative gravity theories. Ideas like Mond-modified Newtonian dynamics, which suggest gravity behaves differently at galactic scales. If galaxies can form without dark matter, maybe we need to rethink how gravity actually works in deep space. But here's a reality check. DF2 is weird, but it's not the only thing out there. We've also discovered galaxies with way too much dark matter. Galaxies where the stars are moving impossibly fast for the amount of visible mass. That means some galaxies hoard dark matter, like dragons guarding treasure, while others like DF2 have almost none. What's going on? Are there two types of galaxies? One family rich in dark matter, one nearly empty, or are galaxies like DF2 just cosmic mutations, rare outliers that reveal hidden truths? It's too early to say for sure, but the fact that multiple galaxies now appear to lack dark matter is enough to challenge the one-size-fits-all model we've been using. And in science, exceptions are gold. They force us to ask better questions. They expose cracks in our assumptions. They remind us that the universe doesn't owe us simplicity. DF2, the ghost galaxy with no dark matter, shouldn't exist, and yet it floats, barely held together, defying the invisible forces that shape the rest of the universe, shining softly like a warning. Not everything fits the mold. Now let's flip expectations completely, because if a galaxy can break the rules, so can a moon. You'd think in a planet-moon relationship, the planet would be the dominant one. Bigger, heavier, more massive. The one with the magnetic field, the atmosphere, the power. The moon just a rock that tags along. But space doesn't care what makes sense, because out near Saturn, there's a moon that has a thick, active, hazy atmosphere, while most planets in the solar system don't. The moon is Titan, and it's one of the strangest objects we've ever studied. Titan is the only moon in the solar system with a full atmosphere, not thin vapor, not a trace, a real dense, pressure-bearing atmosphere. In fact, Titan's atmosphere is denser than Earth's. Let that sink in. A moon has more atmosphere than our planet. But it gets weirder. Titan's atmosphere isn't just a fluke of gas. It has weather, clouds, wind, rain. It forms storms and shapes the landscape. But what it rains isn't water. It rains liquid methane. Titan is like a frozen Earth, reimagined with completely different ingredients: seas, lakes, rivers, but made of hydrocarbons instead of H2O. And yet it's just a moon. Meanwhile, Mercury, a full-blown planet with nearly twice Titan's diameter, has almost no atmosphere at all. Same for our moon. Same for Pluto, which only has a temporary thin haze when it's near the sun. Even Mars, a world 100 times more massive than Titan, has an atmosphere so thin you couldn't survive a second without a pressure suit. So why does Titan of all things have an atmosphere? First, Titan is incredibly far from the sun, over 1.4 billion kilometers away. The surface temperature is around minus 179 degrees Celsius, cold enough to make water hard as rock. But that extreme cold is key. It slows down molecules. Gas particles move sluggishly. So even though Titan has low gravity, only about 14% of Earth's, it can still hold on to light gases like methane and nitrogen because they're not moving fast enough to escape. Second, Titan's atmosphere is mostly nitrogen, just like Earth's, but it also has a few percent methane, which makes all the difference. Methane breaks down under sunlight, forming complex organic molecules. These molecules drift down through Titan's air and create a thick orange haze. That haze blocks sunlight, traps heat, and makes Titan look like a blurry orange ball from space. Now here's where it gets really wild. Titan has dunes, ridges, valleys, storms. Methane rain carves river channels into the icy crust. Radar images from the Cassini mission showed liquid lakes at the poles, some bigger than the Great Lakes on Earth. There's even a methane cycle: clouds, rain, runoff, evaporation, like Earth's water cycle, but made of flammable gas. Let's pause on that. This is a moon with seasons, storms, weather, and liquid on the surface. Not a planet, not a mini Earth, a moon. And here's the kicker. Titan's atmosphere is thick enough to fly in. Seriously, if you flapped your arms while wearing wings, you might get airborne. The dense air and low gravity make Titan the easiest place in the solar system to fly. That's part of why NASA is sending a drone there. The mission, called Dragonfly, is set to launch in 2028. It will fly across Titan's surface, sampling organic molecules, testing chemistry, and searching for the building blocks of life. It'll be the first time we fly an aircraft on another moon, and Titan's thick atmosphere is what makes that possible. But wait, there's more. Scientists think that beneath Titan's icy shell, there may be a liquid water ocean, heated by tidal, flexing from Saturn's gravity. That means Titan might have two layers of liquid. One on the surface, made of methane. Another deep below, made of water and ammonia. Two alien oceans on one moon, with the potential for life in both. It's not just an oddity, it's a prime candidate for astrobiology. If life can form in hydrocarbons, or if there's chemistry happening in that hidden water, Ocean Titan might be the first place we find non-Earth based life. Titan, the only place in the solar system where you could fly like Superman right before you freeze solid in 3 seconds. Here's the thing, we've been searching for life on planets, Mars, Venus, exoplanets, in distant star systems, but the answer might be sitting on a moon, orbiting a gas giant, doing things no moon should be able to do. If a galaxy can exist without dark matter, and a moon can have more atmosphere than planets, then what else is broken? Oh, there's more. The strongest magnetic fields in the universe, and a mysterious force that's tearing apart space-time itself. Among the deadliest and most extreme objects in the universe are magnetars, ultra-dense, hypermagnetized stellar remnants that defy comprehension. These are a subclass of neutron stars, already some of the densest forms of matter outside black holes. But what sets magnetars apart is their mind-bending magnetic fields, the strongest known in the cosmos. A typical neutron star has a magnetic field on the order of 10 to the 12th Gauss. For comparison, Earth's magnetic field is about 0.5 Gauss, but magnetars, they crank that number up to an absurd 10 to the 15th Gauss, 1,000 times stronger than a regular neutron star, 1,000,000,000,000 times stronger than Earth's magnetic field. For scale, the most powerful magnets humans have built, like those in MRI machines or particle accelerators, barely reach 100,000 Gauss. At magnetar intensity, the magnetic field alters the structure of atoms, flattening electron clouds, turning spherical atoms into elongated, cigar-shaped particles. The quantum vacuum around the magnetar doesn't behave normally either. Space itself becomes birefringent, meaning light waves passing through are split and polarized by the magnetic field, an effect called vacuum birefringence, which has actually been observed around magnetars using optical telescopes. So, yes, that joke about magnetars erasing credit cards, it's rooted in real physics. A magnetic field that strong would induce electric currents in nearby objects, distort chemical bonds, and destroy electronics without ever touching them. If you somehow brought a credit card within a few 100,000 kilometers of a magnetar, its magnetic strip would be completely scrambled. If you brought yourself closer, well, your molecular structure would start to come apart long before you arrived. At around 1,000 kilometers, the magnetic field would be strong enough to disrupt the bonds holding your molecules together. You wouldn't just die, you'd be unmade at the atomic level. But magnetars don't just sit there quietly with their terrifying magnetic fields. They're prone to outbursts. As the intense magnetic field shifts and rearranges, it can crack the neutron star's crust, releasing huge amounts of energy in the form of gamma rays, X-rays, and radio waves. These are called starquakes, the cosmic equivalent of tectonic plates shifting on Earth, only made of super-dense nuclear matter. In 2004, a magnetar in our galaxy SGR 180620, located about 50,000 light-years away, released the most powerful flare of gamma rays ever recorded. The burst lasted just 0.2 seconds, but in that flash, it released more energy than the sun emits in 250,000 years. For a brief moment, it actually saturated satellite detectors and caused Earth's upper atmosphere to ionize. Despite being halfway across the galaxy, had it been only a few light years away, It might have wiped out Earth's ozone layer. Or worse, these flares make magnetars candidates for some fast radio bursts, those mysterious millisecond-long cosmic radio signals that repeat. In 2020, astronomers detected an FRB-like burst from the magnetar SGR 1935 plus 2154 located within the Milky Way. It wasn't as powerful as extragalactic FRBs, but it provided the first direct evidence that magnetars can produce FRB-like emissions. This made them one of the leading explanations for the mysterious signals we've been detecting from across the universe. Magnetars are weapons, natural, unstoppable, terrifying weapons, and there may be thousands of them in our galaxy alone. But as extreme as magnetars are, there's something even stranger controlling the fate of the entire universe. Something we discovered by accident, something we don't understand at all. Dark energy. It makes up about 70% of the universe, and we have no idea what it is. Here's what we do know. The universe is expanding. Galaxies are moving away from each other. That much we've known since the 1920s. But in the 1990s, two independent teams of astronomers were studying type Ia supernovae, exploding stars that serve as cosmic mile markers. They were measuring how fast galaxies were receding at different distances, expecting to see the expansion slowing down over time due to gravity. What they found instead shocked everyone. The expansion wasn't slowing down, it was speeding up. Something was pushing space apart with more force than gravity could contain. This wasn't a minor correction. It was a complete rewrite of cosmology. Suddenly, the biggest, most dominant component of the universe wasn't matter stars or black holes. It was an invisible, repulsive pressure spread across all of space, and we had no name for it. So, we called it what it is. Dark energy. Dark because we can't see it. Energy because it acts like a force. A placeholder term for something we don't understand at all. And here's where it gets terrifying. Theoretical calculations of dark energy's strength are off by 120 orders of magnitude. That's not a typo. Our predictions are wrong by a factor of 10 to the 120th power. Literally the worst prediction in the history of physics. Dark energy doesn't just push galaxies apart. It's accelerating the expansion of space itself. And if it keeps accelerating, if its strength increases over time, it could eventually tear the entire universe apart. First galaxies, then stars, then planets, then atoms, until even space and time are destroyed in a final catastrophic unraveling. This scenario is called the Big Rip. We don't understand 95% of the universe. Only 5% of the cosmos is made of regular matter. Stars, gas, planets, people. The rest, dark matter and dark energy. Two things we can't detect, directly can't produce in a lab, and can't fully explain. And here's the kicker. Galaxies are flying away. The void is getting wider. The universe is expanding faster today than it was 1 billion years ago, and there's no sign of it slowing down. In trillions of years, the night sky will grow darker. More and more galaxies will cross the cosmic event horizon, the boundary beyond which their light can never reach us. Eventually, only the local group will remain visible. All other galaxies will redshift out of sight. We've just walked through 5 impossibilities: diamond stars, glass rain, survivor stars, ghost galaxies, moons with atmospheres, magnetars, dark energy, and this is only episode 1. The universe has 37 more slaps to the face of science waiting for us. Dark energy is like The universe decided, I'm going to self-destruct, but really, really slowly. Every second that passes while you read this line, the universe is expanding, and that rate, it's accelerating. We've witnessed the rule breakers. Now it's time for the giants. Black holes so massive, they shouldn't exist. Voids larger than all galaxies combined. And planets wandering alone in eternal darkness. There are black holes. And then there's TON 6 to 18. This one isn't just big. It's impossibly big. So big it shouldn't exist. Not at the time it formed, not in the place it's located, not under any of the models we currently use to explain how black holes grow. But it's real, and it's out there, tipping the cosmic scales at over 66 billion times the mass of the Sun. Let that number settle. That's 66,000 to 1,000,000 solar masses, more than the mass of the entire Milky Way galaxy, packed into a single compact object with a gravitational pull so strong it could swallow our entire solar system in one gulp and not even burp. This is TON 618, a quasar, which means it's a supermassive black hole at the center of a galaxy actively feeding. It devours matter at such a ferocious rate that it releases an enormous amount of energy, outshining every star in its host galaxy combined. In fact, TON 618 is one of the brightest objects in the known universe, even though it's 10.4 billion light years away. That's not a typo. It's so far that the light we see now left the quasar when the universe was only about 3 billion years old. And that's the problem. It's too early. There shouldn't have been enough time in the early universe for a black hole to grow this huge. Not unless it broke every rule we know about how black holes evolve. Let's talk about that. We know black holes form when stars collapse. These stellar mass black holes start small, a few solar masses. Over time, they can grow by accreting gas or merging with other black holes. But growth is slow. It's limited by something called the Eddington limit, a point where the radiation pressure from infalling matter balances gravity. Basically, feed it too fast and it chokes. So for a black hole to reach 66 billion solar masses, it would need a lot of time, way more than a few billion years. And yet TON 618 was already this massive when the universe was still in its early teens. It breaks the timeline. To make it even remotely possible, astronomers have proposed exotic theories. Maybe some black holes form directly from giant clouds of primordial gas in the early universe. Skip the stars. Go straight to the singularity. But even this can't fully account for the size. Maybe TON 618 had a period of hyperfeeding, blowing past the normal limits, gobbling gas so fast that the radiation pressure never caught up. But we've never observed that happening. What we're left with is an object that seems to defy everything we think we know. TON 618 doesn't just test our understanding of black hole growth. It shakes the foundation of cosmology. And here's the truly unsettling part. Its event horizon, the boundary beyond which nothing can escape, is enormous. About 1/300 astronomical units. Across, that's roughly 40 times the distance. From the Sun to Neptune, you could fit our entire solar system inside the event horizon with room to spare. We only found TON 618 because it's bright. It's active, it's feeding, but when it stops feeding, when it becomes a dormant black hole, it'll go silent, invisible. We'd never know it was there. That means for every TON 618, we can see there could be dozens, maybe hundreds, maybe billions more, lurking invisible off the radar, holding galaxies in their gravitational grip. There may be 1 trillion, dormant supermassive black holes scattered across the universe, just sitting there, waiting, invisible, silent. But TON 618 isn't just about size. It's about what happens when you get close to something that massive. Because black holes don't just affect space, they warp time itself. This is called time dilation. And it's not science fiction. It's real, measurable, and proven by observation. Here's the basic idea. The stronger the gravitational field, the more slowly time passes. On Earth, this effect is tiny. Atomic clocks placed at sea level tick slightly slower than those on mountaintops. But the difference is measured in nanoseconds. Near a black hole, the effect becomes extreme. If you were to orbit a supermassive black hole, like TON 618, close to the event horizon time, for you would pass significantly slower than for someone far away floating in interstellar space. We're not talking milliseconds. We're talking about minutes stretching into hours, hours into years, depending on how close you get. This is pure general relativity at work. Gravity isn't just a force, it's a curvature in space-time. Massive objects distort the fabric of reality around them. They bend the geometry of the universe. Light bends, paths bend, even clocks slow down. From the perspective of someone on a spacecraft orbiting near the event horizon, time feels normal. They continue to tick forward at 1 second per second. But from the perspective of someone watching from far away, that spacecraft appears to slow down. Its clocks tick more slowly, its movements stretch out, and as it reaches the horizon, it appears to freeze in place, never actually falling in. This isn't theory. We see this with GPS satellites. Time ticks slightly faster for GPS satellites than it does on the surface of Earth, just due to the difference in gravity. Without correcting for time dilation, GPS systems would become inaccurate by several kilometers per day. Now scale that up. Near TON 618, time dilation would become staggering. If you stayed in a stable orbit just outside the event horizon for a few hours, then returned to Earth, you might find that decades, maybe centuries, had passed for everyone else. This is the plot of Interstellar, the movie where they visit a planet near a black hole, and 1 hour equals 7 years outside. While the specifics were dramatized, the core concept is entirely accurate. Time really does pass differently based on gravity. And here's the truly mind-bending part. For anything falling into TON 618, the universe outside will appear to speed up. If you could look out as you fell toward the event horizon, you might see stars spinning galaxies, evolving cosmic history playing out in fast forward. In the final moments before crossing, external time would accelerate so much that the entire future of the universe could unfold in what appears to be seconds. You'd watch the death of stars, the collision of galaxies, the gradual dimming of the cosmos, all in the blink of an eye. Worried about getting old, just live near TON 618. You'll stay young while the universe ages around you. But here's the thing. As massive as TON 618 is as mind-warping as time dilation gets, there's something even bigger out there. Something that makes even supermassive black holes look tiny. When people think of space, they usually picture stars scattered in a sea of black. But that's only because we live inside a galaxy, one of billions. And most of what we see is crowded, bright, and structured. Zoom out far enough, though, and you'll see something truly unsettling. The universe isn't just full of stars and galaxies, it's also full of nothing, massive yawning expanses of blackness called cosmic voids, holes in the large-scale structure of the cosmos, so big they make galaxy clusters look like ants crawling around the edge of a canyon. And these voids aren't small. We're talking hundreds of millions of light years across, vast spherical regions with almost no galaxies, no matter and no structure at all, just thin whispers of hydrogen, a few scattered atoms per cubic meter, maybe the occasional rogue galaxy floating in isolation, but mostly nothing. Here's the kicker. Cosmic voids make up about 80% of the universe by volume. Let that sink in. Most of space is not galaxies, stars, or dark matter. It's nothing, not just low density, virtually empty. The universe is basically a giant bag of chips. 80% air, 20% content. These aren't random gaps either. They form a pattern, a massive, sprawling cosmic web. When we map the positions of galaxies on the largest scales, we see structure emerge. Galaxies form filaments and clusters, long threads of matter, and in between those threads are the voids. Imagine a 3D spider web with strands of light surrounding vast black bubbles. Now, magnify that by billions of light years. That's our universe. One of the largest known examples is the Buddha's void, sometimes ominously called the Great Nothing. Discovered in 1981, it's about 330 million light years in diameter, and it contains far fewer galaxies than it should. Statistically, a region that size should have thousands. The Buddha's void. It has maybe 60. It's not just a hole, it's a cosmic desert. And it raises a big question. How do you get a region of space so empty? The leading theory is that cosmic voids are the result of gravity and expansion working together. After the Big Bang, tiny quantum fluctuations became slightly denser or slightly less dense regions. Over billions of years, gravity pulled matter into the denser areas, forming galaxies and clusters. While the underdense regions, the voids were emptied out even further, matter gets pulled out. Nothing is left behind. But voids aren't completely dead. They have structure, edges, weak gravitational fields. In fact, galaxies near the edge of voids are often moving away from them as if being pushed out by the expanding, low-density space inside. This isn't a repulsive force, just the effect of higher gravity outside the void, pulling galaxies out of the underdense zone. And here's where things get really strange. Some studies suggest that if you lived inside a void, your measurements of the universe's expansion could differ slightly. Why? Because the geometry of space itself is different in those underdense regions. That means your local universe might seem to expand faster or slower than average, just based on your cosmic address. It's like living in a valley versus on a mountaintop. The curvature and slope change your perception of the landscape. Now, scale that up to galactic proportions. In some cases, galaxies that do exist inside voids called void galaxies are strange in their own right, often smaller, more isolated, less evolved than their counterparts in denser regions. They don't collide as often. They age quietly, like cosmic hermits. And then there's the theoretical wild card. What if some of these voids aren't just accidents of cosmic structure, but evidence of something else? Some fringe theories, still speculative, but interesting, suggest that certain anomalous voids could be the result of early cosmic collisions, maybe with other pocket universes in a multiverse scenario. If another universe bumped into ours in the early stages of inflation, it could have left a scar, a region of lower density, expanding like a bubble in foam. That's probably not the case for most voids. But the fact that we can even ask that question seriously in physics papers tells you how strange these structures really are. Now, if voids are the holes in the cosmic web, then the threads connecting them are the walls. And one of these walls is absolutely massive. It's called the Sloan Great Wall. Discovered in 2003, it's a filament of galaxies stretching roughly 1.37 billion light-years long. That's nearly 3 times the size of the previously known largest structure. It's so big that light would take about 10% of the universe's current age just to travel from one end to the other. Imagine a cosmic spine, a ridge of matter made of millions of galaxies, all gravitationally connected, embedded in a web of dark matter and intergalactic gas. That's the Sloan Great Wall, and it challenges the cosmological principle, the assumption that, on large enough scales, the universe should be homogeneous, smooth, even. But the Sloan Great Wall is anything but smooth. Some scientists have debated whether a structure this large violates the rules, but most evidence suggests such structures can still emerge naturally in a universe governed by cold dark matter and dark energy. Still, the Great Wall blurs the line between structure and anomaly. The universe isn't full, it's mostly missing, and the largest structures we know aren't things. They're places where things aren't. Places so huge, so empty, so quiet, they challenge the idea of what structure even means. Voids, empty, walls, massive. But there's something stranger than both. Galaxies that glow brightly, but are already dead. There are galaxies out there that glow brightly across the cosmos, visible from billions of light years away, packed with hundreds of billions of stars. But they're not making any new ones. Not a single star. They're dead. Or more accurately, they're undead. Zombie galaxies, still shining but no longer alive. One of the most striking examples is Max 2129-1, a massive galaxy located more than 10 billion light-years away. When astronomers first studied it, they expected to find the usual signs of galactic life, star-forming regions, clouds of gas collapsing into new stellar nurseries, the cosmic equivalent of a bustling city. Instead, they found silence. No new stars. No active regions. Just the faint, steady glow of old stars burning out their final reserves. Max 2129-1 is what astronomers call a quiescent galaxy. The term sounds peaceful, almost serene, but in reality, it's a sign of something catastrophic. These galaxies have shut down. They've stopped forming stars billions of years ago, yet they continue to shine because the stars they already have are still burning. They're cosmic fossils, glowing relics from a more active past. What makes Max 2129-1 especially shocking is when it stopped forming stars. Observations suggest it went quiet just 3 billion years after the Big Bang. That's incredibly early. At that time, the universe was young, chaotic, filled with gas and dust. Most galaxies were in their prime, churning out stars at rapid rates. But somehow, Max 2129-1 had already burned through its fuel, consumed or lost all its available gas, and entered a state of permanent dormancy. How does that happen? How does a galaxy run out of star-forming material so early in the universe's history? The answer isn't simple, and it involves several brutal processes that can kill a galaxy's ability to make stars. One mechanism is AGN feedback. That stands for active galactic nucleus feedback. Many massive galaxies host supermassive black holes at their centers. When these black holes feed on gas and dust, they don't just grow, they release enormous amounts of energy in the form of jets, winds, and radiation. This energy can heat the surrounding gas to millions of degrees, preventing it from cooling down and collapsing to form stars. In some cases, the black hole literally blows the gas out of the galaxy, entirely stripping it of its star-forming fuel. Think of it like a cosmic vacuum cleaner in reverse. Instead of sucking material in, it's blasting it out. The galaxy is left with nothing to work with. No gas, no stars. Just the lingering glow of what used to be. Another process is ram pressure stripping. This happens when a galaxy moves through a dense environment, like the hot gas that fills galaxy clusters. As it plows through this intergalactic medium, the pressure strips away its own gas, peeling it off like layers of an onion. Over time, the galaxy loses all its cold, star-forming gas. What's left behind is a dead husk, still visible, still massive, but no longer capable of making new stars. There's also strangulation, a slower, quieter death. This occurs when a galaxy is cut off from its supply of fresh gas. Galaxies don't just live off the gas they're born with. They constantly pull in new material from their surroundings. But if a galaxy falls into a dense cluster or loses its connection to cosmic filaments, that supply is cut off. Without new gas, the galaxy slowly exhausts what it has. Star formation slows then stops. The galaxy fades into dormancy. What's eerie about these zombie galaxies is that they still shine. From a distance, they look alive. They emit light. They have structure. Some even have disc-like shapes, resembling spiral galaxies. But there's no activity, no birth, no growth, just the steady, fading glow of stars that formed billions of years ago, now slowly dying one by one. Maxis 2129-1 is not alone. Astronomers have found dozens of these quiescent galaxies in the early universe. And the more they discover, the more confusing it becomes. Because according to standard models of galaxy formation, galaxies shouldn't be able to shut down this early. They should still be growing, still forming stars, still active. But the James Webb Space Telescope has made the problem even worse. Since its launch, JWST has been peering deeper into the universe than ever before, capturing images of galaxies that existed just a few 100 million years after the Big Bang. And what it's found has stunned astronomers. Massive, mature galaxies. Galaxies that shouldn't exist yet. In the early universe, galaxies are supposed to be small, messy, and chaotic. They're supposed to be assembling, slowly building up mass over billions of years. But JWST has found galaxies that are already enormous, already well-structured, already quiescent. Some of them stopped forming stars less than 1 billion years after the Big Bang. That's not just unexpected, it's model-breaking. One galaxy observed at a redshift of over 10 appears to have a stellar mass close to that of the Milky Way. But it formed when the universe was less than 500 million years old. That's impossible. Or at least it should be. There simply hasn't been enough time for a galaxy that massive to form, exhaust its gas, and shut down. Yet there it is, glowing faintly in JWST's infrared images, defying every prediction. Astronomers are calling it a crisis. JWST hasn't even been operational for 2 years, and it's already forcing cosmologists to rewrite textbooks. The standard models of galaxy formation, the ones built on decades of observations and simulations, are being challenged by what JWST is showing us. Either galaxies form much faster than we thought, or something about the early universe was radically different from what we've assumed. Some scientists are proposing that the first stars, the so-called population 3 stars, were far more massive and short-lived than expected. If these early stars burned bright and fast, they could have enriched the universe with heavy elements much more quickly, allowing galaxies to form and evolve at accelerated rates. Others suggest that supermassive black holes formed earlier than we thought, and their feedback mechanisms shut down star formation much sooner. But no one knows for sure, and that's what makes this so exciting. JWST is not just confirming what we expected, it's showing us things we didn't predict. Galaxies that are too big, too old, too dead, too soon. These zombie galaxies are glowing ghosts from the early universe. They're remnants of a time we don't fully understand. They're shining with the light of stars that formed billions of years ago, stars that will eventually fade, leaving behind dark, invisible masses drifting through space. Dead galaxies, dead suns, dead light. But here's the thing. If galaxies can die, can planets survive without them? Can a world exist without a star to orbit? Can life persist in the cold, in the dark, in the void, between systems? The answer is yes. And those worlds are called rogue planets. Imagine a planet, not orbiting a star, not bathed in sunlight, just drifting through the blackness of interstellar space, alone, cold, and untethered. No day, no night, no seasons, just eternal darkness. These planets exist, and there may be billions of them. They're called rogue planets, and they're one of the strangest classes of objects in the galaxy. They're not bound to any star. They don't reflect light from a nearby sun. They're nearly impossible to detect. But astronomers believe there are more rogue planets in the Milky Way than there are stars. Let that sink in. For every star you see in the sky, there may be 2 or more planets wandering alone in the dark. How do they form? Some are ejected from their home systems during the chaotic early stages of planetary formation. Gravitational interactions between planets can become unstable. One planet swings too close to another, or a giant planet migrates inward, disrupting orbits. In these interactions, smaller planets can be flung outward at high speeds, escaping the star's gravity entirely. They're kicked out, exiled, left to wander the galaxy forever. Other rogue planets may form in isolation without ever being part of a solar system. In dense, star-forming regions, gravitational collapse can create objects too small to ignite fusion and become stars, but large enough to be considered planetary mass. These free-floating objects drift alone from the moment they form, never knowing the warmth of a sun. One of the most intriguing examples is Ogle 2005 BLG3 9tail b, a planet discovered through gravitational microlensing. It's located about 21,000 light-years away, and it's roughly 5.5 times the mass of Earth. It orbits a red dwarf star, but at such a vast distance that it receives almost no heat. Its surface temperature is estimated at around 220 degrees, colder than Pluto. For all practical purposes, it's a frozen wasteland. But here's the twist. Despite being frozen on the surface, Ogle 2005 BLG 399 may have liquid water beneath its icy crust. How? Internal heat. Even without a star, a planet can generate heat from radioactive decay in its core. Elements like uranium, thorium, and potassium release energy as they decay, and if the planet has a thick enough atmosphere or ice shell, that heat can be trapped. Over time, it can melt the inner layers of ice, creating a subsurface ocean. This is not speculation. We see it in our own solar system. Europa, one of Jupiter's moons, has an ocean of liquid water beneath its ice shell, kept warm by tidal heating. Enceladus, a moon of Saturn, has geysers shooting water into space, evidence of a hidden ocean below. If moons can have subsurface oceans, so can rogue planets. And if they have liquid water, they might be habitable, not on the surface, where temperatures are hundreds of degrees below freezing, but deep underground in warm, dark oceans, life could theoretically exist. It wouldn't rely on sunlight. It would rely on chemosynthesis, the same process that sustains life near hydrothermal vents on Earth's ocean floor. Microbes that extract energy from chemical reactions, from hydrogen sulfide, from methane, from minerals, dissolved in water. A rogue planet with a subsurface ocean could sustain life for billions of years long after its original star has died. It could drift through the galaxy, carrying its hidden biosphere, completely invisible to the outside universe, a world alive in the dark. But let's talk about what it would be like to live on a rogue planet. If you were standing on the surface, assuming you could survive the cold, you would see nothing, no stars. Or rather, you'd see stars, but they'd be faint, distant pinpricks scattered across the sky with no pattern, no constellations, no familiar reference points. There would be no sun to mark time, no day-night cycle, no seasons, just an endless, unchanging night. If the rogue planet once had moons, they might still be there, orbiting silently. But without sunlight, you wouldn't see them unless they glowed faintly from their own internal heat. The sky would be black. The ground would be frozen. The only light might come from auroras if the planet had a magnetic field and happened to pass through a region of ionized gas. And yet this lonely existence might not be rare. Current estimates suggest there could be 2 billion rogue planets in the Milky Way for every star. That means there are hundreds of billions, possibly trillions, of these worlds drifting through space. Some are gas giants, bloated and massive. Others are rocky, Earth-sized frozen solid. A few might have atmospheres thick enough to trap heat. A handful might even have oceans. Some rogue planets might carry their own planetary systems. If a planet is ejected with enough mass and gravity, smaller moons or planets could remain bound to it, orbiting in the darkness. Imagine a mini solar system with no sun, just a massive rogue planet at the center, with smaller worlds circling it, all drifting together through interstellar space. The night sky on such a world would be completely black. No central star, no bright light, just the faint glow of distant galaxies and the occasional passing comet. If intelligent life somehow evolved on such a world, they might never discover the concept of a star. They might think the universe was just darkness, punctuated by faint lights that never moved. Detecting rogue planets is incredibly difficult. They don't emit light. They don't transit in front of stars. The only way to find them is through gravitational microlensing, a technique that detects the brief bending of light when a massive object passes in front of a background star. It's rare, fleeting, and requires perfect alignment, but it works, and it's how we've found most of the rogue planets we know about. In 2020, astronomers detected what may be the smallest rogue planet ever found, roughly the mass of Earth. It was drifting alone far from any star invisible, except for the brief moment it bent the light of a distant sun. That discovery confirmed what many had suspected. Rogue planets aren't just gas giants, they're rocky worlds too. Worlds like Earth, wandering the galaxy, homeless and alone. Some rogue planets might not stay rogue forever. Occasionally, one might drift close to a star and be captured into orbit, becoming part of a new system. In other cases, they might pass through a planetary system, disrupting orbits, scattering debris, and then moving on, leaving chaos in their wake. And here's the philosophical kicker. Life doesn't need a sun. It just needs liquid water, an energy source, and the right chemistry. If rogue planets can provide all three, then the galaxy might be teeming with hidden life drifting unseen through the void, not around stars, not in the warm glow of a sun, but in the cold and the dark, in places we've only just begun to search. Survival without sunlight. That's the story of the rogue planets. But some planets don't wander alone. Some orbit, not one sun but two. In 2011, NASA's Kepler Space Telescope confirmed something that had only existed in science fiction: a planet orbiting two stars at once. It was called Kepler 16b, and for Star Wars fans, it was instantly recognizable. This was Tatooine, a real world with twin suns. Kepler 16b is located about 200 light-years away in the constellation Cygnus. It orbits a binary star system, two stars locked in a gravitational dance, circling each other every 41 days. The planet itself orbits both stars at a distance of about 0.7 astronomical units, completing one full orbit every 229 days. It's a gas giant, roughly the size of Saturn, cold and uninhabitable. But it's real, and it proves that planets can form and survive in binary systems. Before this discovery, many astronomers believed that binary stars were too chaotic for planets to form. The gravitational forces from two stars pulling in different directions should have disrupted the protoplanetary disk, preventing planets from coalescing. But Kepler 16b defied that assumption. It showed that planets can form around binary stars, and they can remain stable for millions, possibly billions of years. What makes these circumbinary planets so fascinating is their complexity. Orbiting two stars means dealing with a three-body problem, one of the most notoriously difficult challenges in physics. The gravitational interactions between the planet and both stars are constantly shifting, creating a dynamic, ever-changing orbital environment. Yet somehow, Kepler 16b holds together. Its orbit is nearly circular, stable, and predictable. Imagine standing on the surface of such a planet, assuming it had a solid surface, which it doesn't, but let's pretend. You would see two suns in the sky. Sometimes they'd be close together, rising and setting almost simultaneously. Other times, they'd be separated, crossing the sky at different times. One might be larger and brighter, the other smaller and dimmer. Together, they'd cast double shadows, two silhouettes stretching across the ground in different directions. Depending on the orbital alignment, you might even witness eclipses, one star passing in front of the other, dimming the sky temporarily, casting strange shifting shadows. The light levels on the planet would fluctuate constantly, creating a complex, unpredictable pattern of brightness and darkness. No simple day-night cycle, just a chaotic dance of light and shadow. Kepler 16b is not alone. Since its discovery, astronomers have found dozens of circumbinary planets. Some orbit close to their stars, receiving enough heat to be warm or even hot. Others are far out, cold and dim. A few are rocky, though most are gas giants. One system, Kepler 47, contains 3 planets orbiting a binary star, the first known multi-planet circumbinary system. These discoveries raise an intriguing possibility. If circumbinary planets are common and binary stars make up more than half of all star systems in the galaxy, then a significant fraction of planets in the universe might orbit twin suns. That means double sunsets, twin shadows, and eclipse shows might be far more common than we ever imagined. But Kepler-16b's orbit is relatively simple compared to what some planets experience. If you want extreme look at Uranus, this gas giant in our own solar system has one of the strangest tilts in the solar system. Its axis is tilted 98 degrees, meaning it essentially rolls around the sun on its side. The result? Seasons that last 42 years. Yes, you read that right. 42 years. When it's summer at Uranus's North Pole, that pole points almost directly at the sun. It experiences continuous daylight for 42 Earth years. Meanwhile, the South Pole is plunged into darkness, a polar night that lasts just as long. Then, half an orbit later, the roles reverse. The South Pole gets 42 years of sunlight, and the North Pole freezes in the dark. This creates temperature extremes unlike anything on Earth. Even though Uranus is far from the sun and receives very little heat, the prolonged exposure to sunlight on one hemisphere while the other remains dark causes significant atmospheric changes. Winds shift, cloud patterns emerge, storm systems develop, all on a timescale measured in decades. For any life that might hypothetically exist on such a world, survival would require adapting to these incredibly slow but dramatic cycles. Imagine a winter that lasts an entire human lifetime. Imagine summer being just as long. There would be no quick seasonal changes, no spring thaw after a few months, just slow, relentless transitions over decades. Uranus's extreme tilt is likely the result of a massive collision early in its history. Models suggest that a large object, possibly the size of Earth, struck Uranus and knocked it onto its side. This same impact may have disrupted its internal heat flow, which is why Uranus is colder than Neptune, despite being closer to the Sun. But extreme axial tilts aren't limited to Uranus. Some exoplanets may have even stranger orientations, tilted beyond 90 degrees, rotating backward relative to their orbit. Others might wobble their axes, precessing over time, creating seasons that shift not just yearly, but over thousands of years. Combine a tilted planet with an elliptical orbit, and you get even more chaos. A planet that swings close to its star during one hemisphere's summer and far away during winter would experience temperature swings far more extreme than anything Earth sees. Summers could be scorching, with temperatures soaring as the planet approaches its star. Winters could be brutal, with the planet freezing as it retreats to the far end of its orbit. And if that planet orbited two stars, like Kepler-16b, the complexity multiplies. The seasons would depend not just on the planet's tilt and orbit, but also on the relative positions of the two stars. One star might dominate during one part of the year, the other during a different season. The result would be a climate system so complex, so dynamic, that predicting weather would be nearly impossible. Here's the thing: a 4-month winter on Earth feels long. A 42-year winter on Uranus is unimaginable, but it's real, and it's happening right now in our own solar system. So, when you think about planets, don't just picture Earth-like worlds with gentle seasons and predictable climates. Picture planets rolling on their sides orbiting twin suns drifting alone through the dark or shining brightly while making no new stars. Picture zombie galaxies, rogue worlds, and suns that never set, because we've just walked through the giants, the strange, the unexpected. Now we move into the truly inexplicable. Fast radio bursts that repeat, magnetars that fire beams of death, galaxies that collide but whose stars never touch, and a star that appears to be older than the universe itself. In 2007, astronomers reviewing old data from the Parkes Radio Telescope in Australia stumbled upon something they couldn't explain: a burst of radio waves, incredibly bright, incredibly brief, less than a millisecond long, and it came from deep space, far beyond our galaxy. At first they thought it was a glitch, interference from a microwave oven maybe, or a passing satellite. But the signal had all the hallmarks of something cosmic. It was dispersed, meaning it had traveled through ionized plasma across vast distances. The delay between high and low frequencies told them exactly how much matter the signal had passed through. This wasn't Earth-based noise. This was real. They called it the Lorimer burst, named after the astronomer who discovered it. And it was the first detection of what we now call a fast radio burst, or FRB, a cosmic mystery that more than 15 years later, we still don't fully understand. FRBs are strange for several reasons. First, they're insanely powerful. In just a few milliseconds, a single burst can release as much energy as the sun emits in an entire day. That's an absurd amount of power packed into a fraction of a second. Second, they come from all over the sky, scattered randomly across the universe. No pattern, no preferred direction, just sudden flashes of radio energy appearing and disappearing without warning. For years, astronomers assumed these bursts were one-time events, cataclysmic explosions, something that destroys the source in the process. Maybe colliding neutron stars, maybe collapsing black holes, maybe something even more exotic. But then, in 2016, everything changed. A burst was detected that repeated. It was called FRB 12-2, and it didn't just flash once and vanish. It kept coming back. Dozens of bursts from the same location in the sky. This was a game changer, because if the source could repeat, it wasn't being destroyed. It was something persistent, something stable, something that could fire off these massive bursts again and again without blowing itself apart. Astronomers traced FRB 12-102 to a dwarf galaxy more than 3 billion light-years away. Using interferometry, they pinpointed the source to a tiny region within that galaxy, possibly near a young supermassive black hole or a dense cluster of neutron stars. But even with this precision, the exact mechanism remained a mystery. Then came another discovery. Some repeating FRBs follow patterns. FRB 180916 J0158 plus MER65, for example, displays a 16-day cycle. For 4 days, it's active, firing off bursts at irregular intervals. Then it goes silent for 12 days. Then it starts again, like clockwork. This rhythmic behavior suggests something rotational, maybe a neutron star spinning on its axis with bursts only visible when a certain emission region points toward Earth, like a lighthouse beam sweeping across the ocean. Or maybe it's a binary system where the geometry of the orbit affects when and how the bursts escape. No one knows for sure, but the periodicity is real, and it's one of the biggest clues we have. In 2020, astronomers detected something even more significant. A fast radio burst from within our own galaxy. It came from a known object, a magnetar called SGR 1935 Plubo 2154. located about 30,000 light years away. This was the first time an FRB-like signal had been traced to a specific type of object, and it confirmed what many had suspected. Magnetars, those hyper-magnetized neutron stars we talked about earlier, can produce FRBs. But here's the catch. The burst from SGR 1935 plus 2154 was much weaker than the extragalactic FRBs we've detected. If it had been billions of light years away, we probably wouldn't have seen it at all. So, either distance makes these bursts look brighter than they are, or the extragalactic FRBs are coming from something even more powerful than magnetars. Magnetars themselves are terrifying objects. They're neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. These fields are so intense they can warp the vacuum of space itself, creating a phenomenon called vacuum birefringence. And when a magnetar's crust cracks, it releases a starquake, a violent rearrangement of matter that sends shockwaves through the star's surface and launches bursts of gamma rays, X-rays, and sometimes radio waves into space. In 2004, a magnetar in our galaxy unleashed the most powerful flare ever recorded. It was called SGR 180620, and it was located about 50,000 light years away. The burst lasted just 0.2 seconds, but in that instant, it released more energy than the sun emits in 250,000 years. The radiation was so intense, it actually ionized part of Earth's upper atmosphere, despite being halfway across the galaxy. If it had been just a few light years away, it might have stripped our ozone layer or worse. That event showed just how violent magnetars can be. And if they can produce bursts that powerful, they might be responsible for at least some of the FRBs we're detecting. But not all of them, because some FRBs are far too energetic even for magnetars. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, has revolutionized the field. This radio telescope located in British Columbia monitors a huge swath of sky continuously. Since it started operations, it's detected hundreds of FRBs, more than all previous telescopes combined. And it's revealed just how common these bursts really are. Thousands of FRBs might be happening every day all across the sky. We're just not seeing most of them because they're pointed in the wrong direction or they're too faint. Crime has also shown that FRBs can be used as cosmic probes. Because radio waves get dispersed as they travel through ionized gas, the amount of dispersion tells us how much matter the signal passed through. This lets astronomers map the distribution of gas between galaxies, measure the density of the intergalactic medium, and even test predictions about the missing baryon problem, the fact that we can't account for all the normal matter the universe should contain. So, FRBs aren't just a mystery. They're a tool, a way to study the universe's structure, its magnetic fields, its hidden gas. Every burst that reaches Earth carries information about the space it traveled through, the conditions it encountered, the environment it came from. But we still don't know what causes most of them. Magnetars are one answer, but probably not the only one. Some FRBs might come from neutron star black hole collisions. Others might be caused by exotic processes we haven't even considered. And a few, the ones that repeat on precise schedules, might hint at something even stranger. Are they natural? Almost certainly. But the precision, the power, the mystery, it's no wonder that early speculation included the possibility of artificial signals, alien beacons, propulsion systems, communication arrays, There's no evidence for that. None. But the fact that it was even discussed seriously tells you how bizarre these signals are. FRBs are questions wrapped in radio waves. They arrive without warning, vanish without explanation, and leave behind more mysteries than answers. Aliens number magnetars, maybe, Hotel Trivago. But as strange as FRBs are, there's something even weirder. Galaxies that collide, but whose stars somehow pass right through each other, like ghosts. When you hear the word collision, you probably picture destruction. Two cars crashing, two planets smashing into each other, stars exploding in violent impacts. So, when astronomers say that the Milky Way is going to collide with the Andromeda Galaxy in about 4.5 billion years, it sounds catastrophic, like the end of everything. But here's the thing. The Sun will be fine. Earth will probably be fine. Most stars in both galaxies will be fine. Because when galaxies collide, the stars don't actually hit each other. Let that sink in for a moment. Two galaxies each, containing hundreds of billions of stars, can pass through one another, and the odds of any two stars colliding directly is almost zero. It sounds impossible, but it's true. And the reason is simple. Space is mostly empty. In the Milky Way, the average distance between stars is about 5 light years. That's roughly 30 trillion miles. Stars are tiny compared to the distances separating them. So when two galaxies merge, it's less like two solid objects crashing and more like two swarms of bees passing through each other. Some bees might get close, but actual collisions, incredibly rare. What does collide, however, is gas, and gas collisions are spectacular. Take the Antennae galaxies, two spiral galaxies located about 45 million light-years away in the constellation Corvus. They're in the middle of a merger, and the results are stunning. Long tidal tails of stars and gas stretch out from both galaxies, twisted and pulled by gravitational forces. These tails, shaped like antennae, are the result of the galaxies ripping material away from each other as they pass. But while the stars mostly avoid each other, the gas clouds don't. When interstellar gas collides, it compresses, heats up, and collapses under its own gravity. This triggers massive bursts of star formation, lighting up the collision zone with thousands of new stars. These are called starburst galaxies, and they're some of the brightest, most active regions in the universe. In the Antennae galaxies, this starburst is in full swing. Hubble Space Telescope images show glowing clusters of newborn stars, each cluster containing tens of thousands of suns, all formed in the chaos of the collision. Over time, many of these stars will explode as supernovae, enriching the surrounding gas with heavy elements and triggering even more star formation. But the collision isn't over. The two galaxies are still dancing around each other, locked in a gravitational embrace. They'll continue to interact, pulling and stretching for hundreds of millions of years. Eventually, they'll merge completely, forming a single larger galaxy. Most likely, an elliptical galaxy, round and featureless, with no defined spiral arms. This is the fate of the Milky Way and Andromeda. In 4.5 billion years, they'll collide. The first pass will distort both galaxies, flinging out tidal tails of stars and gas. Then they'll swing back around, colliding again and again each pass, bringing them closer together. After about 1 billion years of these repeated encounters, they'll finally settle into a single merged galaxy. Astronomers have nicknamed it Milkdromeda. During this process, the Sun and its planets will likely survive. They might be flung to a different part of the new galaxy, pushed outward into a distant halo, or pulled closer to the galactic center. But direct collisions, not likely. The solar system will continue to orbit undisturbed by the chaos around it. What won't survive is the view. The night sky will be completely different. As the galaxies merge, the familiar constellations will shift and distort. New stars will blaze to life. Gas clouds will glow with the light of starburst regions. And at the center of it all, two supermassive black holes, one from each galaxy, will spiral inward toward each other. When supermassive black holes merge, they don't just combine quietly. They release gravitational waves, ripples in space-time, that propagate outward at the speed of light. These waves carry energy, and as the black holes spiral closer, they lose angular momentum, eventually colliding in a violent event that could be detected by future observatories, like the Laser Interferometer, Space Antenna, or LISA. LISA is designed to detect gravitational waves from massive sources, like merging supermassive black holes. When the Milky Way and Andromeda collide their central black holes, Sagittarius A and M31 will eventually merge. And if there's anyone around to witness it, they'll see the signature of two monsters becoming one. But galaxy collisions aren't just about stars and black holes. They're also about dark matter. And that's where the bullet cluster comes in. The bullet cluster is one of the most important observations in modern cosmology. It's a pair of galaxy clusters that collided at high speed, passing through each other about 150 million years ago. When astronomers studied the aftermath, they found something shocking. The gas and the stars had separated. The hot gas, visible in X-rays, had slowed down during the collision, creating a shock wave. But the galaxies themselves, along with most of the mass, had kept moving. Gravitational lensing, the bending of light around massive objects, showed that the majority of the mass was not where the gas was. It was where the galaxies were. This separation is direct evidence for dark matter. The gas, which is normal matter, collided and slowed. But the dark matter, which doesn't interact with anything except gravity, passed right through unaffected. The galaxies embedded in halos of dark matter kept moving because most of their mass is dark. This observation effectively killed many alternative theories of gravity. If gravity worked differently, without dark matter, the mass should have stayed with the gas. But it didn't. The mass moved with the galaxies, proving that there's something invisible holding them together. Something we can't see, but we can measure through its gravitational effects. The bullet cluster is proof that dark matter is real. Not a trick of gravity, not a misunderstanding of physics. Real invisible matter making up most of the universe's mass. So when galaxies collide, it's not like a Hollywood explosion. It's a slow, graceful dance that takes hundreds of millions of years. Multiple passes, gravitational interactions, gas compression, star formation, and eventually merger. It's chaos on a cosmic timescale, but chaos that's predictable, measurable, and beautiful. The collision is over. Now we turn to things that shouldn't exist but somehow survived. Things that should have died but didn't. There's a star in the constellation Libra that has astronomers scratching their heads. It's called HD 1Ortino 283, but is better known by its nickname, the Methuselah star. and for a while, it appeared to be older than the universe itself. Let that sink in. A star estimated to be 14.46 billion years old, existing in a universe that's only 13.8 billion years old. That's not just a small error. That's a fundamental problem. Either the star's age is wrong, or the universe's age is wrong, or maybe we don't understand something basic about how time works. HD 140283 is a subgiant star located about 190 light years away. It's not particularly bright or massive. What makes it special is its composition, specifically its lack of metals. In astronomy, metals means anything heavier than helium, and HD 140283 has almost none. Its iron content is less than 1/250th that of the Sun, which means it formed from gas that hadn't been enriched by previous generations of stars. This makes it a population 2 star, one of the oldest types of stars in the universe. Population 2 stars formed early when the universe contained mostly hydrogen and helium, with just trace amounts of lithium. The first stars, population 3 stars, were even more primitive, made entirely of primordial gas. But they were massive, short-lived, and none have been directly observed. HD 140283 is as close as we can get to that early era. So, how did astronomers determine its age? They use stellar evolution models, which calculate how stars change over time based on their mass composition and luminosity. By measuring the star's brightness, temperature, and chemical makeup, they could estimate how long it had been burning. The result was shocking: 1446 billion years, plus or minus 0.8 billion years. Even at the lower end of that estimate, the star was still older than the universe. That's a problem. But the issue wasn't with the universe's age. It was with the star's distance. Stellar age calculations depend heavily on knowing how far away the star is, which determines its intrinsic brightness. Early measurements of HD 140283's distance came from ground-based parallax observations, which had significant uncertainty. In 2013, astronomers used the Hubble Space Telescope to get a more precise parallax measurement. With better data on the star's distance, they recalculated its age. The new estimate, 13.7 billion years, plus or minus 0.7 billion years. That brought it just within the age of the universe. Barely. At the upper end of the error bars, it's still pushing the limit. But statistically, it's no longer a paradox. The Methuselah star is old, incredibly old, but not impossibly old. Still, the fact that it came so close to breaking the universe's age limit is significant. It highlights how difficult it is to measure stellar ages with absolute precision. Small errors in distance composition or brightness can throw off age estimates by hundreds of millions of years, and it reminds us that our cosmic timeline, while well established, still has uncertainties. HD 140283 isn't the only ultra-old star. Astronomers have found others with similarly extreme ages. BD plus 1317 to 3248, He, 1523, Jodo 9001, and several other metal-poor stars push the boundaries of what we think is possible. Some of these stars formed less than 500 million years after the Big Bang, making them relics from the universe's infancy. These ancient stars are time capsules. They preserve the chemical fingerprints of the early universe before multiple generations of stars had enriched the cosmos with heavy elements. By studying them, astronomers can test models of nucleosynthesis, galaxy formation, and the rate of cosmic chemical evolution. But there's another wrinkle. The Hubble tension. The Hubble constant, which measures the rate of the universe's expansion, has two different values depending on how you measure it. Observations of the cosmic microwave background give one number. Direct measurements using supernovae and variable stars give another slightly higher number. If the higher value is correct, the universe would be younger, and that would bring the Methuselah star back into conflict. This tension is one of the biggest unresolved problems in cosmology, and stars like HD Martino 283 sit right on the edge of that debate. So, is the Methuselah star older than the universe? No, probably not, but it's close enough to make us double check our math. And in science, that's valuable. Now let's shift from ancient stars to frozen moons, specifically Enceladus, one of Saturn's moons, a tiny icy world that's doing something it absolutely shouldn't be doing. It's shooting water into space. In 2005, NASA's Cassini spacecraft flew by Enceladus and captured something extraordinary: geysers, massive plumes of water vapor, and ice particles erupting from cracks near the moon's south pole, blasting hundreds of kilometers into space. This was completely unexpected. Enceladus is only 500 kilometers wide, roughly the size of Arizona. It should be frozen solid, geologically dead. But it's not. It's active. And those geysers are evidence of something even more remarkable: a subsurface ocean. Beneath Enceladus's icy crust, there's liquid water, kept warm by tidal heating, the same process that powers volcanic activity on Jupiter's moon Io. As Enceladus orbits Saturn, the planet's gravity stretches and compresses the moon, generating friction and heat in its interior. That heat melts the ice, creating a global ocean beneath the surface. And that ocean is in contact with a rocky seafloor. Cassini's instruments detected molecular hydrogen in the plumes, a chemical signature that suggests hydrothermal activity. On Earth, molecular hydrogen is produced when seawater reacts with hot rock in deep-sea hydrothermal vents, the same process that supports entire ecosystems on Earth's ocean floor. If Enceladus has hydrothermal vents, it has an energy source. If it has liquid water, it has a solvent. If it has organic molecules, which Cassini also detected, it has the building blocks of life. That makes Enceladus one of the most promising places in the solar system to search for extraterrestrial life. And we don't even have to land on it. The geysers bring samples from the ocean directly into space. A future mission could fly through the plumes, collect particles, and analyze them for biosignatures. That mission is already being planned. It's called Dragonfly, and it's set to launch in 2028. But Dragonfly is heading to Titan, another moon of Saturn. For Enceladus, other missions are being proposed. The Enceladus Orbilander, for example, would orbit the moon, fly through the plumes multiple times, and eventually land near the geysers to study them up close. If life exists in Enceladus's ocean, we might find it within the next 2 decades. We've been searching for life on Mars for decades. We've sent rovers, landers, orbiters, all looking for signs of ancient microbes in dried up riverbeds. But maybe the answer isn't on Mars. Maybe it's on a tiny moon of Saturn, hiding beneath a shell of ice, thriving in a dark ocean, completely cut off from sunlight. Life doesn't need the sun. It just needs water, energy, and chemistry. And Enceladus has all three: old stars, active moons. But there's one more thing, something massive invisible and undeniable, the great attractor, and it's pulling us toward it whether we like it or not. The Milky Way is moving, not just orbiting within the local group, not just spinning around its own axis. It's being pulled, dragged through space at a speed of roughly 600 kilometers per second toward a region of the sky we can barely see. Something massive is out there, something so gravitationally dominant that it's hauling our entire galaxy along with thousands of others toward it, like debris caught in a cosmic current. This invisible gravitational monster is called the Great Attractor, and for decades, it remained one of the most mysterious structures in the universe. The story begins in the 1970s when astronomers started mapping the velocities of galaxies in our cosmic neighborhood. They expected to see galaxies receding uniformly due to the expansion of the universe, with slight variations caused by local gravitational interactions. What they found instead was a massive coherent flow. Hundreds of galaxies, including our own, were moving in the same direction toward a specific point in space near the constellations Norma and Triangulum Australe. This wasn't random motion. It was organized. Something was pulling. The region responsible for this pull is located about 150 to 250 million light years away, centered behind what astronomers call the zone of avoidance. This is the part of the sky obscured by the dense plane of the Milky Way itself. Gas dust and billions of stars block our view, creating a cosmic blind spot. For years, astronomers couldn't see what was causing the Great Attractor because it was hidden behind our own galaxy's glare. But they knew it was there. Gravitational effects don't lie. The velocities of galaxies around this region showed clear signs of a massive gravitational pull, strong enough to affect structures hundreds of millions of light years across. Estimates suggested the Great Attractor contained the mass equivalent of tens of thousands of galaxies, all concentrated in a relatively small volume of space. To peer through the zone of avoidance, astronomers turned to X-rays and infrared observations. These wavelengths can penetrate dust more effectively than visible light. Using instruments like NASA's Rosat X-ray telescope and ground-based infrared surveys, they began mapping the hidden structures behind the Milky Way. What they found was remarkable. At the heart of the Great Attractor region lies the Norma cluster, one of the most massive galaxy clusters nearby. It's not a single object, but a dense concentration of galaxies, gas and dark matter, all gravitationally bound together. The Norma cluster, along with several other nearby clusters, forms a gravitational focal point, a cosmic drain pulling matter inward from all directions. But the story doesn't end there. In 2014, astronomers made an even bigger discovery. The Great Attractor itself is part of something much larger, a supercluster called Laniakea. Laniakea is a vast structure spanning over 520 million light years, containing more than 100,000 galaxies. Its name means immense heaven in Hawaiian, and it's an appropriate description. Laniakea encompasses the Milky Way, the Virgo supercluster, the Great Attractor, and everything in between. It's not just a cluster, it's a network of clusters, all gravitationally connected, all flowing toward a common center of mass. The Milky Way sits on the outskirts of Laniakea, being pulled inward along with everything else. Our motion isn't just local, it's part of a larger cosmic flow, a river of galaxies streaming through space, guided by gravity on scales we're only beginning to comprehend. But even Laniakea isn't the final answer, because beyond the Great Attractor, there's something else pulling, something even more massive. It's called the Shapley Supercluster, located about 650 million light years away. This is one of the most massive structures in the observable universe, containing tens of thousands of galaxies concentrated in a relatively small region of space. Some astronomers believe that the Great Attractor is just a waypoint, a local gravitational dip in a much larger flow toward the Shapley Supercluster. In this model, our motion isn't determined by the Norma cluster alone. It's determined by the combined gravitational influence of multiple superclusters, all pulling in different directions, creating a complex velocity field that shapes the motion of galaxies across hundreds of millions of light years. This is where things get really strange. Because when you map the motions of galaxies on these scales, you start seeing patterns that don't quite fit. One of the most controversial findings is something called dark flow. In 2008, a team of astrophysicists announced that they had detected a large-scale motion of galaxy clusters that couldn't be explained by known structures. They studied the cosmic microwave background, specifically looking at how its light gets scattered by hot gas in distant galaxy clusters. This scattering, called the kinematic Sunyaev-Zeldovich effect, or KSZ effect, leaves a faint imprint that reveals the motion of the clusters. What they found was unexpected: a coherent flow of hundreds of galaxy clusters, all moving together in the same direction toward a region of sky near the constellation Centaurus. The motion extended over distances of more than 2.5 billion light years, far beyond where such flows should exist, according to standard cosmological models. They called it dark flow, and the implications were staggering. If dark flow is real, it suggests that something beyond the observable universe is pulling on the matter we can see. Maybe a massive structure just beyond our cosmic horizon, maybe an anisotropy in the early universe, a remnant of cosmic inflation that created uneven density distributions on the largest scales. Or maybe, in the most speculative scenarios, gravitational influence from another universe entirely. Not everyone is convinced. Some astronomers argue that dark flow is a statistical artifact, a quirk of how the data was processed. Follow-up studies using different data sets have produced mixed results. Some replicate the signal, others find nothing. The debate continues. But whether dark flow is real or not, it highlights something fundamental. The universe is not uniform. It's structured, dynamic, and filled with gravitational influences that stretch across unimaginable distances. The Great Attractor pulls. The Shapley Supercluster pulls. And somewhere hidden, beyond the edge of what we can see, there might be even larger structures, even more massive concentrations of matter shaping the motion of galaxies in ways we're only beginning to understand. Here's the thing: we're not standing still. The Earth orbits the Sun at 30 kilometers per second. The Sun orbits the Milky Way at 220 kilometers per second. The Milky Way falls toward Andromeda at 110 kilometers per second, and the entire local group is being pulled toward the Great Attractor at 600 kilometers per second. Layer upon layer of motion, each driven by gravity, each part of a larger cosmic dance, and we're just passengers, moving through space, carried by forces we didn't choose, toward destinations we can't escape. The Great Attractor doesn't care about us. It doesn't care about our galaxy. It's just gravity, doing what gravity does, pulling matter together, shaping the universe one galaxy at a time. This story is almost over. But the universe is never done with mysteries, because the Great Attractor pulls, dark flow pushes, and we're standing at the edge of what we can see, the edge of what we can know, the edge of the observable universe itself. There's a limit to how far we can see, not because our telescopes aren't powerful enough, not because space ends somewhere, but because of time. Light travels at a finite speed, and the universe has a finite age. That combination creates a boundary beyond which nothing can ever reach us. That boundary is 46.5 billion light years away. That's the edge of the observable universe. Wait, how can the edge be 46.5 billion light years away if the universe is only 13.8 billion years old? The answer is expansion. When a photon left a distant galaxy 13 billion years ago, that galaxy was much closer. But while the light traveled toward us, space itself stretched. By the time the photon arrives today, the galaxy has been carried much farther away. The light is ancient, but the source has moved. This is why the observable universe spans 93 billion light years across, even though it's only 13.8 billion years old. Everything within that sphere is detectable. Everything beyond it is not. But here's the problem. Just because we can see something doesn't mean we can reach it. Thanks to dark energy, the universe isn't just expanding, it's accelerating. Most galaxies we see are already receding faster than light, not moving through space that fast, but carried by space itself. And there's no speed limit on expansion. That means many galaxies we see right now are already beyond reach. Light they emit today will never reach us, not in a billion years, not ever. This creates the cosmic event horizon, a boundary beyond which objects disappear from our future permanently. And that horizon is shrinking. Every day more galaxies cross that line. In a few trillion years, everything outside our local group will vanish. Future observers will see an empty sky, just one massive merged galaxy. No distant lights, no cosmic microwave background, no evidence the universe ever expanded. They'll conclude the universe is static, eternal, unchanging. And they'll be completely wrong. But the evidence will be gone, erased by expansion. We're living in a brief window when the universe is still visible, when its history is still readable. A trillion years from now, that window closes forever. What lies beyond the edge? Probably more of the same. More galaxies, more stars, more structure. The cosmological principle suggests the universe looks roughly the same everywhere, but we can't prove it. We can only see our bubble. Some theories suggest eternal inflation, where our universe is just one bubble in an infinite multiverse. Each bubble, a separate cosmos with its own physics, but we can't see them. They're beyond the horizon, forever out of reach. This is it, the 93 billion light-year sphere around us. That's our entire reality. Everything we can ever see, measure, or know, not a limitation of technology, a limitation of physics itself. Let's step back. We've walked through 42 things that shouldn't exist. Diamond stars, glass rain moving at hypersonic speeds, planets hotter than their stars, zombie galaxies glowing without life, rogue worlds drifting alone, twin suns with orbiting planets, neutron stars spinning 700 times per second, frozen moons shooting water into space, repeating radio bursts from nowhere, magnetars that could kill from across the galaxy, colliding galaxies whose stars never touch, a star nearly older than time itself, the great attractor pulling us into darkness, and the absolute edge of everything. 42 impossibilities, real, measurable, undeniable. Here's the message. We don't understand this universe. Not really. Every time we think we've figured it out, space shows us something stranger, something that breaks our models, something that forces us to start over. The universe doesn't owe us answers. It doesn't owe us simplicity. It just exists. Vast, complex, chaotic, beautiful. And our job is to look up, observe, and try to understand, however imperfectly. Next time you see the night sky, remember, behind every star is an impossibility. Behind every light is a mystery. And maybe, just maybe, 42 isn't all of them. Maybe we've barely started. Maybe the universe has 1,000 more waiting, 1,000,000, more than we can count. The universe where physics comes to be broken, and us still looking up, still asking why, still searching for truth in the darkness. Because that's what we do. That's what we've always done. And that's what we'll keep doing as long as the stars still shine.